Assalamu alaikum everyone. Uh, Today we will learn about Chuck converter. So this is one of the converter type that can be used in both buck and boost operation. So here is the simple circuit diagram of the converter. So we have the input voltage is here, and then we have a inductor L1, and then we have a capacitor here C. This is called the coupling capacitor. Sometimes I may refer it to CC in the short form of a coupling capacitor. And then we have L2 or the second inductor, and then we have a filter capacitor near the load, and then here we have the load, and we have a switch here. Now this can be either connected to position 1 or in position 2. Now, unlike the buck boost converter that we have covered in our previous lectures, here in the Chuck converter, the energy storing element is the capacitor C, the coupling capacitor C. So this is basically transferring the energy from the input to the load. We'll see it how it works. So when the switch is connected to position number 1, at that time we have basically the input is connected to L1 and it is short circuited here. So L1, so the current is flowing, basically the input current is flowing through L1 and then it's coming to the negative terminal of the source. And here we have this capacitor which was pre-charged. Now in the steady state operation, don't consider the case in the beginning of the circuit when it's run. So in the steady state condition, the capacitor was charged, so it will basically discharge and then the current will flow like this. So we'll have a current flow for the input, it's like this, and then for the second part the current flow is like this. And the AC part of the current, AC part of this current, if I denote it as I2, so the AC part of this I2 will flow through this capacitor, and the DC part of this I2 will flow through this resistance. Now from the current direction look, if we define the output voltage polarity like this, then you can see that the output voltage polarity will be negative because the current is entering from the bottom of the circuit. Okay, so this is the condition when the switch is connected to position number 1, and at that time VL1 or the voltage drop across switch 1 is basically V in, because we have VL1 like this. This is our VL. So the voltage across inductor L1 is the VL1, which is equals to V in. This is our V in. Okay, and then for inductor L2, our VL2, or this is the voltage across the inductor VL2, which is equals to minus VC minus V naught. So the negative of the capacitor voltage, you can apply the KVL versus voltage loop to get the value of the voltage across the inductor L2. Now when the switch is connected to position number 2, at that time you are basically charging the capacitor. So on the left hand side, this is the flow of the current, so you are basically charging the capacitor like this, and then in the second part you have basically this inductor, so the current flow will continue to be like this, and some part will obviously go like this. So in this particular case, the voltage drop across L1 is V in minus Vc, so this is our Vc. So if you apply KVL, you get the voltage across inductor 1, VL1 is V in minus Vc. For inductor 2, VL2 is basically the voltage which is appearing across across the output of the voltage if we apply the KVL. So now, as we know that we have the voltage drop across the inductor, we know what is the voltage drop across both of these inductors during these two states, whether it's connected to switch 1 or whether it's connected to position number 1 or in position number 2. You know what's the voltage across the inductor. And then our obvious approach, the first approach that we are always following is to calculate the gain equation. That means the relationship between the output voltage and the input voltage. And to do that, the equation that we are always using is the Volts-Seg balance equation, which means that the integration of the inductor voltage over the whole time period is basically 0. So for the time when it is connected to position number 1, during that time our this is for L1. So for considering for inductor 1, if you integrate voltage drop across inductor 1 for the whole time period, that means from 0 to T on, this equals to V in, and from T on to T, it's equals to V in minus Vc. So if you integrate it, so you have this integration, and if you do the algebraic manipulation, then you end up with a equation which relates your V in and Vc. That means you have a relationship between your capacitor voltage Vc and the input voltage V in with respect to the duty cycle, like this. Now once you know the relationship of the voltage, you can write the relationship of the current. That should be the opposite of the coefficient that you are multiplying here. So that should be the opposite here. So the inverse of it is 1 minus t. So the IC is basically 1 minus t multiplied by I in. So you have a relationship between Vc and IC with respect to the input of the voltage and the current. And then if you use the Volts-Seg balance equation for inductor 2L2, then for inductor 2, during the time from 0 to T on, we derive that VL2 is basically minus Vc minus V naught. That means minus Vc minus V naught, and you integrate it from 0 to T on, plus for the time in stage 2, VL2 is minus V naught. So you have minus V naught, you integrate it from T on to T, which is equals to 0. And after the algebraic manipulation, you end up with another set of equations where the relationship is between Vc and the output voltage. So you have a relationship between the capacitor voltage and the output voltage, and once you know the relationship between Vc and V out, you can calculate the relationship between IC and I out. That should be the opposite of this part. Okay, so now you have in equation number 1, you have a relation between Vc and V in, and equation number 2, you have a relation between Vc and V out. So if you know, from equation 1 and 2 by the algebraic manipulation, you end up with V out equation, which is basically like minus d divided by 1 minus d multiplied by V in. So this is our gain equation. So V out divided by V in, this is the gain, or the voltage gain, which can be related or written like minus t divided by 1 minus t. So this is the same multiplying factor that you have seen in the Buck-Boost converter. That means when the d value is less than 0.5 at that time, so let's say the d value is 0.2, so the numerator part is minus 0.2 and the denominator part is 1 minus 0.2, which is equals to 8. That means the multiplying factor, so this is 0.8, so this is operating as a Buck converter when you have a duty cycle less than 0.5. That means it's a step down operation. But if you change this duty cycle to more than 0.5, let's say this is 0.6, so in the numerator you have minus 0.6 now, and in the denominator part you have 0.4. That means it is now using it can be now used as a stepping up operation, and the voltage, output voltage can be increased than the input voltage. And the current equation, that will be the opposite of this factor here, because the multiplication of the output current and the output voltage should be the same as the input voltage and the input current, considering that if you consider all the circuit parameters as ideal, that means there is no loss. If there is no loss, that means the output power should be equals to the input power, and that also says that the current should be, the coefficient here should be the opposite of the voltage coefficients. So how this circuit is built, this is the example of how it is built in real life. So we have the input voltage here, P in, and then we have the inductor L1. Now these switches, these two position can be replaced by a transistor and a diode if we place it like this. So whenever we are giving a gate pulse in this switch, it can be MOSFET, it can be transistor. So whenever we are giving the gate pulse here, so whenever this MOSFET is on, that means that your current is flowing like this, and then this on means that this diode is basically reversed bias. So this diode is reverse bias because you have basically whenever, because this is short circuited, so this diode is reverse bias. That means this positive terminal here comes here. So this positive of the capacitor, so this is connected here. That means the cathode of the diode has more potential than the anode. That means this diode is reverse bias. So on the right hand side, your circuit is like this, which is exactly the same from the fundamental circuit diagram as shown here. In the second stage, when this transistor is turned off, at that time this part is basically open. So this part is basically open. At that time this diode is forward biased, so the diode is conducting, and this is identical to the position when the to second position of the circuit operation. So now you have the current flow like this. So this is the same as this part. So this is how it's built in a real environment. So I have built a very simple Simulink model here. As you can see, this represents the Chuck converter. So you can play with this model. You can add current measurements here. You can simply copy it. For example, if you want to see what's the current flowing through this L1, you can copy this current sensor and then paste it here, and then add this current measurement like this. So you replace this and then you add the here, and then you can see the output. For instance, you can increase the number of input in this scope. You can simply double click here and then go to the settings. You can give number of input as 5, and then let's say this is our IL2. You can write this is IL2. So like this way you can add voltage and current probes here to see what's the wave shape of the voltage and current that's look like. So if we run the circuit, then we will be able to see whether it's a buck operation or a boost operation. So in this particular case, our duty cycle was, the D value was 0.6. That means that it should be a stepping up operation. Our input is 100 volt. That means the output should be more than 100 volt. And if we see in the output, then we can see that so this is the output here. So it's here, and you can see clearly that the this green line is basically the output voltage, which is first of all negative value, and the input was 100 volt positive value, so the output is in the opposite direction, output voltage, and it is more than the magnitude of the output voltage is more than the input voltage, and this red line is the output current, the inductor current, this IL2. So this is the inductor current IL2. Okay. Okay, and then this is the gate pulse in the top. Here you can see that this is the time when the gate pulse is off, and this is the time when you have 1 in the gate pulse. That means the transistor is on at that time, and during this time the transistor is off. Now when during the time when the transistor is basically on, the inductor current will start increase, because the inductor is storing the energy, so the inductor current should increase at that time. So whenever your transistor is on, at that time your inductor current is rising, and after that, so this is the IL1, so this is the inductor current through the inductor 1, which is defined as IL1. And when your transistor is off at that time, so whenever your transistor is off at that time, this inductor and this input source, both of them is energized in this capacitor here. So during that time, this inductor current should drop, as you can see from here, it's going down. Okay, and in case of the capacitor current, now the capacitor current, if you look at here, then for some time the capacitor current is flowing like this. That means for the time when this switch is turned on, when this transistor is turned on, during that time the capacitor is discharging, and for the other phase the capacitor is charging basically. So the capacitor current is the I coupling capacitor. So for certain time you have a positive I coupling capacitor, and for certain time it is negative, it is basically discharging. Okay, and this inductor current is basically the same as the capacitor current for the time when this capacitor and inductor is connected. That means in the second phase, this IL2 is the same as the capacitor current, and you can consequently derive. So once you get this inductor current, the AC part of the inductor current will flow through the filter capacitor, and the DC part will flow through the load. And you can also, using the same technique, you can find out what's the current wave shape, what should be the current wave shape through this diode, because for the case when this switch is turned on, for the time when the switch is turned on, that means whenever you are having a current conduction like this, when the switch is turned on, this diode is reverse bias. That means during that time the current through the diode should be 0, and whenever your switch is turned off, at that time your diode is actually flowing. That during that time current in the across the diode should be, so you have this current one is charging like this, and the other is going like this. So from this you can calculate the current that is flowing through the diode. Okay, so if you look at the transistor current, so for the time when the for the time when the switch is on, during that time you are having a transistor current, and when this gate pulse is off, at that time the transistor current is basically 0, and the other one is the IC, or the, so this part is the IC part, or the filter capacitor current that is flowing here. Okay, so yeah, so our next task is to calculate what's the minimum value of this L1 and L2. So these are the circuit parameters, so we need to calculate what's the value, what should be the value of this L1, L2, C coupling and C filter. So we have to, we need to derive the equations, and in the numerical problems we need to calculate what should be the value, what should be the minimum value of this inductor in order to have a continuous current operation. So as you look into the inductor current wave shapes, so if you look into the inductor current wave shapes, then you see that the inductor current is basically for certain time it's going up when the switch is turned on. So that means during the on duration of the switch, your inductor current is rising, and during the off duration the inductor current is falling. So based on these, so you can derive what's the maximum value of this inductor current, L1 max. So the maximum inductor current in the inductor 1 is basically the DC part of this inductor current. That means the DC part is somewhere here. So the DC part of the inductor current plus this half of this delta or peak to peak value of this inductor current. So that means this DC part here, and then half of this DC part. So this comes again from the slope equation. So this is the slope which comes from L di dt formula, because if you look at here, so if you look at here, so the current, so it's L di dt is the voltage across the inductor, or VL. So from here you can get the DI part. So the DI part is basically VL. So DI can be written as VL divided by L multiplied by dt, like this. So this VL is the same as V in during this time. So the slope is V in divided by L1. So this is the slope multiplied by the time duration. So the time duration in the on time, so T on, you can write T on as duty cycle D multiplied by T. So that is what is written. So you have done the similar, you have followed the similar approach in the previous converter derivations. So once you know IL1 max, you can find IL1 minimum, which should be the negative of it here, because now we have the DC component of the IL1 minus the half of the peak to peak value of the inductor current. Now during the continuous operation for minimum value of IL1 at the boundary, this minimum IL value should be 0. So now we say that this part should be 0. So you write 0 is equals to this, and then from here you calculate a relationship between the input I in. So you replace IL with I in, because IL and I in for that time is the same. So you replace IL1 with I in, and you previously calculated the relation between I in and I out with duty cycle. So you replace I in with relationship with I out and duty cycle. You replace V in with V out and duty cycle here, and then you do the manipulation, and you end up with L1 mean equation, which says that L1 mean should be this value. To calculate L2 mean, you follow basically the same approach. The only difference here is that now this slope is linked with the output voltage, and this is corresponds to the off time of the transistor, and the off time is basically T off, which can be also written as 1 minus D multiplied by T. So this is the off time, and during that time the slope of the IL2 is V out divided by L2. So if you look at here, so your VL2 is V out, basically the amplitude is V out, so the slope is this comes from here. So IL2 minimum should be the DC component of IL2 minus half of the peak to peak value of the IL2, which can be written as half of V out divided by L2 multiplied by the T off time, which can be written as 1 minus T multiplied by T. So during the at the boundary of this continuous in this continuous operation, this value should be 0. So you write 0, and then IL2 can be written as I out during the off time. During the off time, IL2 can be written as I out, and you have V out here, and I out can be written as V out divided by R. So from there you have the relationship of L2 mean. So what should be the minimum value of the inductor? Okay, and then we need to derive what should be the value of the coupling capacitor. That means this C value. So whenever we are calculating the C values, we follow the approach of the ripple factor. So how should be the voltage ripples here, and what should be the voltage ripples in the output? So the voltage ripples in the output, that basically is defined by the filter capacitor, and the voltage ripple here in the coupling capacitor, that will define the value of the C. Okay, so the smaller the value of the C, the faster it will discharge. So the faster this stored energy in the capacitor will be discharged. That means that you will have higher ripple. Now we need to calculate what should be the minimum value of this capacitor. In this case, this coupling capacitor, what should be this value in order to have a certain ripple factor. Now for the output ripple, output voltage ripple, normally that is kept at a very minimum level, typically 0.1%, or in some cases it can be 1%, so it's very small, whereas there is no definite requirement that it should be very small here. The ripple in the coupling capacitor is not recommended to have extremely small, because if your ripple is very small, that means you need to have a very big capacitor here as the coupling capacitor. On the other hand, this ripple is not important, because we are focusing on the output voltage should be fixed. So the voltage ripple in the coupling capacitor, that will not be a very big issue, and typically in the design it's kept around 10, 20, 30%. So in that cases, if you are told to have a certain percentage of the voltage ripple in the coupling capacitor, if the ripple factor is higher, that means you can basically have a lower value of the capacitance. That means you can reduce the cost and also the size of the converter. Now we'll see how to calculate this capacitor value. So our IC, or the current in the this capacitor, coupling capacitor current, is basically like this. So in one case, when this capacitor is basically charging, so during the time when it is charging, at that time the capacitor current is basically the same as IL1. So this part is the same as IL1, and when this capacitor current is basically discharging, at that time the capacitor current is the opposite direction, and it's the same as IL2. So this is the whenever the capacitor current, so in the position number 1, if you can recall from the beginning of the slides, in the position number 1 you have operation like this. So in the position number 1, the capacitor is discharging like this. The capacitor current should be the same as IL2. Okay, so now this opposite part, this comes from the direction of the current flow. So if you assume like this, then this IL2 will be like this. So yeah. So the average value of this IL2 or the DC part of this IL2 is basically I out, and the DC part of this IL1 is basically I in. So from either of these two relationships, so if you consider this part of the stored charge in the capacitor, or from this part, from either of these equation or either of this part, you can basically derive the relationship between the capacitor value and the ripple factor. So this dq, or the amount of charge that is stored here, is basically, so you can take the DC part here, and as we know that this small triangle and this small triangle are identical, so if you swap these two, so basically the amount of charge that is stored here is I naught, because this is the output current, so I naught multiplied by the time when this switch is on. So the switch is on can be written as T on, which can be also written as dt, and at that time the current here is the same as the output current, so it's I naught dt, which can be written as V out divided by R d multiplied by 1 over F, which is replacing T with 1 over the switching frequency. So this coupling capacitor C should be higher than this value, and normally this V out divided by dVc, or this is the inverse of the ripple factor. This is typically this ripple content is around 10 to 20% of the output voltage. Okay. Finally, we need to know what should be the value of the filter capacitor, or C out. And then to do that, our approach is, what is the current actually flowing through the capacitor current. First we need to know what's the capacitor current. So the capacitor current is basically the AC component of the IL2. So if we know the IL2, so this is our IL2, and the DC part of the IL2 is basically the output current here. The IL2 has two parts, one is the DC and the other is the AC part. The DC part flows through the resistance and the AC part flows through the capacitor. The AC part means that is the ripple part of the IL2 that will flow through the capacitor. So IC should be the ripple part of the IL2. So IC can be written like this, and then our next approach is to calculate the area of this shaded part. So this is the amount of charge that is transferring. So for certain time we have a charge transferred here, and then the other part will go in this direction. So you can again calculate either of this area of this triangle. And to calculate the area here, so this part, so you have done this calculation in the previous converters. So this part is basically T by 2. So we have T by 2 here. So half T by 2, half is for the area of the triangle. So it's half T by 2 is the base, and then the height is basically half of the ripple peak to peak value. So half of this delta IL2. And after the algebraic manipulation, replacing T with the switching frequency F, and then replacing with this delta IL2 with the output voltage and the inductor value, that means the slope and the time when the duration when it is off, at that time you can define as 1 minus d multiplied by t. So from this relationship you end up with a ripple factor like this. So from this ripple factor, normally this dV by V naught, this value is kept as 0.1%, or if the specification says it's 1%, then you know what should be the value of dV by V naught, and then your task is to calculate what's the value of C. But prior to that, you should of course calculate the minimum value of L2. So again, if you see the approach, every time first we are calculating what's the duty cycle. So the first thing is the duty cycle, and the duty cycle is always related to the input voltage and the output voltage. So you may ask to design a converter, and in that cases you will be said what should be the input voltage and what should be the output voltage. So you know the input voltage and output voltage. From there you can calculate the value of the D. So that is the first approach you follow every time. And then your next design approach is to calculate the value of the L. So the value of the L for continuous current operation, you can calculate the value of the L from these equations. So you can calculate the value of the L, or once if you understand the operation of the circuit, if you think a bit closely, then you can see that for certain time, for example, whenever you are calculating the L1 value, so L1 is linked with input current, or L1 is linked with V in, and L2 is linked with output current, or is linked with V out. So by considering these parts, you can basically calculate what should be the value of L1 and L2. And once you have the value of L1 and L2, then you can calculate the value of the C, or the capacitor. Okay, so that's the end of today's lecture. I will also post this Simulink file. You can play with the Simulink file. You can check with the theory part whether you understand the theory part well or not. You can play with this Simulink file to have a much better understanding about the theory of this subject. So with this, I would like to conclude today's session. If you have any question, we will of course address it in the discussion class. Thank you very much.